In the earlier lecture, we already raised the question, when is these numbers, pi x, reciprocals of expected return time, when are these numbers form a probability on S? We already saw that for finite state space Markov chains that is so. So in this lectures, we are going to eventually really get an answer to that question. Of course, while doing that, we have to bring in some other techniques, in particular very similar to those random variables ZRs, which were basically sequence of gaps between successive visits to a particular state y. We are now going to need to introduce another sequence of random variables which will do the following. Between successive gaps of visits to y, it will count the number of visits to a different state x, and will prove as kind of similar result for this new sequence, and that will be pretty handy for finally getting an answer to the question as to when are the numbers pi x form a probability on x on the state space S. So remember that we are considering an irreducible recurrent Markov chain. We have defined these quantities pi x, 1 over expected time to return to x starting from x. And the question that we raised is in the earlier lectures is these numbers pi x, we know they are between 0 and 1. So when do these numbers form a probability on S? We saw that if the state space S is finite, then it's always a probability, but in general what happens? So to handle this question, we need to prove another result which is very similar to some of the results that we have seen. This result will play a crucial role in answering the questions that we just asked about the numbers pi x. So with random variables, remember the random variables try for r greater than or equal to 1 and zry for r greater than or equal to 0 were earlier defined. Try's were successive visits to y, and zry's were the gaps between these successive visits. So this was for a fixed state y. Now what I do is we define another sequence, but now another state x would get involved. So this new sequence is going to be called z suffix rx y. So it depends on both the states x and y for r greater than or equal to 0. So let me give the definition. So the 0th one is defined to be the number of k's between 1 and t1y such that xk equals x. And for r greater than or equal to 1, it's the same thing. We want xk to be equal to x, but we count how many k's are there with xk equal to x, which are strictly larger than try and less than or equal to tr plus 1y. So if you look at this definition, then basically what they do is the following. z0xy counts the visits to x from time 1 until the time of the first visit to y. So we are looking at all k between 1 and t1y. On the other hand, for r greater than or equal to 1, remember the k varies between try and tr plus 1y, excluding try but including tr plus 1y. So it means that it counts visits to x strictly after time of the rth visit to y up to and including the time of r plus 1th visit to y. So it's basically trying to count the number of visits to x between successive visits to y. So what we're going to show is that these random variables defined as z, r, x, y, they satisfy a property very, very similar to the properties that were proved for the zry's earlier. So here's a proposition. For any initial distribution mu, the random variables zr, x, y, you only look at random variables indexed by r greater than or equal to 1, then they are identically distributed, and the common distribution is the same as the py distribution of z0 xy. Now the idea of the proof is very similar to the analogous fact that we proved about the original zry's, but let me therefore just give an outline of the proof. So for any r greater than or equal to 1, if you look at the event z0 xy is j0, etc., etc., zr xy is jr, you can break up this event as a disjoint union over integers n1, n2, nr plus 1 strictly increasing of events where you also put in conditions on t1y value, t2y value, etc., etc. So that's basically what's written here. Now think of this composite event that we have written including the values of try, different try's for r equal to 1 to r plus 1. Part of that is going to be thought of as history. Which part? Namely the part that starts from z0xy equal to j0 etc., goes all the way up to try equal to nr. So there all that is involved is the history up to time n, which is just n1 plus n2 plus nr. You can clearly see that that part of the event involves only history up to that time with xn equal to y, because we are assuming that try is nr. And the remaining part of the composite event can be thought of as future over time n plus 1 to nr plus 1. Now use the standard thing, probability of A intersection B is probability of A times probability of B given A, and then use Markov property, and then add over all these integers n1, n2, nr plus 1 to get this final identity that the original event, the p mu probability of that is the p mu probability of what we considered as history part, and then conditioned on the history, the conditional probability of that future simply becomes py probability that z0xy is jr. You can see that why that is so. It's just simple Markov property. Now, so what we have done is we have written the original event z0x equal to j0 etc., zrx equal to jr as p mu probability of all these things up to zr minus 1, and then the zr part has come out as the probability that z0xy equal to jr. Now you can, since this holds for every r greater than or equal to 1, you can now complete the proof by induction. So now let's define this quantity theta yx to be ey expectation of z0xy. So this is the expected, roughly speaking, this is the expected number of visits to the state x for a chain starting at y up to the time that the chain returns to y for the first time. So that's what it is. This is of course going to be clearly, from what we have just now proved, this is going to be the common expected value of the zr r greater than or equal to 1 under any p mu. So applying strong law of large numbers to the non-negative IID sequence zrxy for r greater than or equal to 1, you do get with p mu probability 1, you have this thing that 1 over r I equal to 1 to r zixy goes to theta yx as r goes to infinity. Now this sum goes from I equal to 1 to r. We would like to have the sum from I equal to 0 to r, but that's triviality. Observe that the 0th random variable z0xy is bounded by definition by t1y, which is actually finite with probability 1 under p mu. So if you divide that one single random variable by r and let r go to infinity, then with probability 1 that goes to 0. So there is no harm in adding that one extra term. So combining this with the earlier result, we actually get 1 over r times the sum from 0 to r now goes to the same limit theta yx as r goes to infinity with probability 1, p mu probability 1 for every mu. Note that y was arbitrarily fixed originally, and now we have fixed another state x arbitrarily. So what it means is that the above result holds for any pair of states x, y in S. Now what this really says is that following. I mean, one way is to look at the mathematical formula, but try to understand what it really says. What it really says is that whatever be the initial distribution mu, the number of visits to a state x up to and including the r plus 1th visit to another state y divided by r converges with probability 1 to the numbers theta yx, and the theta yx, that number depends only on x and y and nothing else. So now we return to the question, when is these numbers pi y in S, when do these numbers form a probability on S? Since the numbers, all these numbers are between 0 and 1, essentially it boils down to when is this sum equal to 1. So that's what I have said. So recall that since Ey of Ty lies between 1 and infinity, both bounds included, so pi y lies between 0 and 1, both bounds included. Also notice that pi y equals 0 if and only if Ey Ty is infinite, because that's the only way pi y would be 0. So therefore, if for all y in S, Ey ty is infinity, that is expected time to return to y starting from y is infinite, for every state y, then all the pi y's would be 0. And there is no hope that pi y's can be a probability, because they have to add up to 1 and all of them are 0. So one thing is immediate, that for pi y in S, this set of numbers to be a probability on S, you must have at least one y in S for which this expectation Ey ty is finite. What we'll show is that this is actually sufficient. That is, if there is even one y in S for which Ey ty is finite, which will force pi y to be positive, even if this happens for only one y, we'll show that in that case the numbers pi y do give a probability. Okay, so for that we make a definition. So here we are dealing with a property that for some y in S we want Ey ty to be finite. So there is a name for this particular property. A state y is said to be positive recurrent if Ey ty is finite. Remember, recurrence was that ty should be finite with py probability 1, whereas we say that y is positive recurrent if not only ty is finite with probability 1, its expectation also is finite. Of course, a trivial remark is that if you already have Ey ty finite, that forces the py probability that ty is finite is 1. So a positive recurrent state is of course trivially recurrent. So now let's try to proceed towards what we just claimed. So assume that there is some y in S such that Ey ty is finite. So in other words, in terms of the definition, there is at least one positive recurrent state y. Now fix such a y and recall those sequences try and zry that we have already considered before. Also recall that for any sequence x, we have the sequence zrxy of random variables which we have defined before. Now suppose we define theta yx as we have defined before is the Ey expectation of z0xy, then what we have proved is this. We have just proved it. Now recall, we had earlier proved with p mu probability 1, nyn goes to infinity and nyn over n goes to pi y's n goes to infinity. So from that we deduce, so essentially we know that 1 over r I equal to 0 to r zry ziy, that goes to theta y x as r goes to infinity. If we let it instead of r, if we put in n and y, then let's see what happens. Well, we start with 1 over n r equal to 0 to n and y zry. Then we have 1 over n, so we want to have 1 over nyn, so that's a matter of multiplying and dividing by n and y, which has been done in the second step. Now the second factor goes to theta yx and the first factor goes to pi y, and therefore the product goes to pi y into theta yx. So far so good. Now let's try to understand what is this sum on the left hand side whose limit after dividing by n we obtained. What is this sum? The sum r equal to 0 to n and y. It looks complicated. Z r x y. What is this? Just a little thought and you should be able to see what this gives you, this sum gives you is counts all the visits to x up to time n plus the visits to x during the time period n plus 1 to t n and y plus 1. Just think about it and you'll be able to convince yourself that's exactly what it is. Of course, this additional part, the number of visits to x during the time period n plus 1 to t n and y plus 1 can be at most the duration of this time interval, which is t n and y plus 1 minus n, and that in turn is bounded by t n and y plus 1 minus t n and y. Now recall what we had earlier proved. We had earlier proved that with p mu probability 1, try by r converges to a limit Ey ty as r goes to infinity. And our assumption is that this limit is a finite limit. So dr plus 1 y over r converges as r goes to infinity with probability 1 to a finite limit. Now from that, just a little bit of calculus, this would clearly imply, just convince yourself, that if you look at the tr plus 1 over y minus try, that divided by r has to go to 0 with probability 1. So just convince yourself. If a sequence over r converges to a finite limit, then the differences of the sequence divided by r has to go to 0. That's all it's saying. So now with nnx denoting the number of visits to x up to time n, we therefore obtain that with p mu probability 1 as n goes to infinity, you look at this object, what was our earlier sum zrx for r equal to 0 to nny, subtract from that nnx, which is exactly the number of visits to x up to time n, that divided by n, of course that's greater than or equal to 0, but the top we have seen is bounded above by t nny plus 1 minus t nny. So therefore the ratio is divided is less than or equal to this ratio, second ratio, and that second ratio is can be written as by again multiplying and dividing by nny, you get this. And why does this last thing go to 0? That is because the first factor goes to 0 from what you've just now seen, and nny over n goes to pi y, which is of course a quantity less than or equal to 1. So therefore we have this, that this goes to 0. So what we have therefore proved is that this difference between our sum and nnx, that divided by n goes to 0. We already know that this sum over n goes to pi y times theta y over x with probability 1. So nnx over n must have the same almost sure limit, because the difference between these two goes to 0 is what we have seen. Now we bring in something else. At the same time, we also know that the quantity nnx over n, we had proved it for y, but y was arbitrary, so it's also true for x. nnx over n goes to pi x as n goes to infinity. That's true for any x. So on one hand, we already knew that nnx over n goes to pi x, but what we have just proved also gives us the limit pi y into theta y x for the same quantity nnx over n. So therefore we must have the two things, the two quantities pi x and pi y into theta x must be equal. So that's exactly what the proposition says. Of course, here an important part is that y is a special y for which you are assuming that ey ty is finite, equivalently pi y is positive. So if that is true for some y in S, then for every x in S, pi x has to be equal to theta y x into pi y. So that means any other pi x can be seen to be pi y times theta y x, where y is that special y. Suppose now the hypothesis of the above proposition is true. That is, there is at least one state y for which pi y is positive. That means y is positive recurrent. The proposition then says that this is true, pi x equal to theta y x into pi y for all states x in S. Now suppose we add it over all x's, add both sides over all x's. Well, what do we get? On the left hand side we get sum of pi x, x in S. On the right hand side, pi y is free of x and we are adding over x. So we get pi y, and then in front of that sum of theta y x over all x in S. But theta y x by definition is expected ey expectation of z0 x of y. So if I add theta y x's over all x's, then it becomes the expectation of the sum of the z0 x y's, sum over all x's. Here just notice that interchange of expectation and sum, this sum could be infinite because S is not assumed to be finite. So exchange of this expectation and possibly infinite sum is valid because all the terms are non-negative. The z0 x's are all non-negative random variable for various x's. So therefore we can interchange, and this is what we get, that summation theta y x over all x in S is this thing. Now recall that z0xy counts the number of visits to x till time 1, from time 1 till the time of first visit to y. So if I add all these z0x's over all states x in S, what do we get? We get ty. So because between the time and ty, you count how many times the chain visits x and then add these counts over all possible states x, you end up counting the entire time. So this is exactly ty. So combining that with the earlier result, what we get expression of pi x, x over x, we already saw that this is equal to the second expression in this equality, and then the second expression, the first factor of the second expression is ey of ty, because that sum of z0x's over all x in S is just ty. So what you end up getting is ey ty into pi y, but that by definition is 1, because ey ty is a finite quantity and pi y is just its reciprocal, so the product of the two is 1. So what have we proved? We have proved that summation pi x, x in x is 1. So that gives us this proposition immediately, which we have just proved. In an irreducible recurrent Markov chain, if ey ty is finite, equivalently pi y is positive for some y in x, even one y in x, then the numbers pi x, x in x. Now, it was clear already that ey ty is infinity, equivalently pi y is 0. Suppose that is the case for all y in S, then we knew that pi y in S cannot be a probability on S, because all of these numbers are 0. So we already observed that for these set of numbers pi y varying through S to be a probability on S, it was absolutely necessary that one pi y must be positive for at least one state y in S. Pi y positive is equivalent to ey ty being finite. What we have just shown is that it's not just necessary, it's actually sufficient, in the sense that if on the other hand we have shown that at least one y is there for which ey ty is finite, equivalently pi y is positive, then it turns out in that case pi x, x in x is indeed a probability. So what we have just proved can now be summed up in the following manner. Fix an irreducible recurrent Markov chain. What we have shown just now is that the set of numbers pi x, x in x, x in S is a probability on S if and only if there is at least one y in S with positive value of pi, positive pi y, which of course is equivalent to expected return time to y starting from y is finite. But that does not yet rule out the possibility that pi x may equal 0 for some x in S. All it says is that if one of them is positive, then the numbers together add up to 1. That's a probability. But some of the other numbers of the other pi x's could still be 0. We will prove a result which will actually rectify this. And what it will imply is that, no, if pi y is positive for some y, then indeed none of the other pi x's can be 0. All the pi x's are actually positive in that case. So that's the result that is about to come. So later what we are going to prove is that in any irreducible recurrent chain, if ey ty is finite, expected return time to y starting from y is known to be finite for some y, this property actually holds for all states. So it cannot be that an isolated property holding for one state but not holding from, once we have an irreducible recurrent chain, then either this property of expected return time being finite holds for all states. So in these lectures we have actually finally been able to completely prove the necessary and sufficient conditions under which for an irreducible recurrent Markov chain, the numbers pi x, as x varies over various states, these numbers actually form a probability. And the result that we have essentially proved is that if your closed irreducible recurrent Markov chain has at least one state y for which the expected return time is finite, then of course we saw that that's a necessary condition, but we have just now proved that it's actually sufficient condition. But of course, what we are going to show later is something more that happens under that assumption that there is one such y with finite expected return time. We'll show that something more happens, which will give us more facts about these numbers pi x's.